Good afternoon, everyone, and I hope that most of you have made on time to join this webinar. I am very glad to welcome you at this 19th webinar from the EU Africa R&D facility. And my name is Ewelina Dobrowolska, and I am Earth observation scientist working in Serco in Italy. And in this webinar, I will like to introduce the PolInSAR techniques and the concept for agriculture monitoring and mapping. Okay, now I will switch my camera off to make this presentation nice and clean. At the beginning, I would just to briefly introduce the concept of the webinar and also provide you some with some logistics information. So in this webinar, as you may know, we will focus on PolInSAR topic and applications of this technique in agriculture with reference to African continent to the possible extent. And I would also like you to remind you to keep your microphone and camera turned off during the session because to ensure that there will be a stable bandwidth and stable connection without any interruptions. So the webinar will last about 1 hour and will be recorded. So to be uploaded then later on YouTube. And within a few days, you will find it there and also on our portal. So the webinar is divided into following sections. First of all, to all newcomers to the activity, I will provide a brief introduction to EU Africa R&D facility project and its activities. Then I will introduce the topic of today's session, and I will provide a brief introduction and refresh the knowledge of SAR principles and the techniques used in agriculture monitoring. And then we will move forward to more details about polarimetric SAR interferometry principles and applications. I will also provide you an overview of available data from space, providing information on agriculture from with fully polarimetric products. And at the end, also a few case studies on monitoring agricultural problems will be demonstrated as well, but this will be based on literature review. So this webinar will have a format of more theoretical one, but of course, some practical insights will be given as well. Then at the end of the session we will have time for live Q&A session. And you can type your questions in the Q&A tab or in the chat within this meeting, and I will have a look at them at the end of this webinar to answer them. So just to provide you a bit of the context, I would just mention what is EU Africa. And EU Africa stands for African Framework for Research, Innovation, Communities and Applications. And it is an activity developed by ESA, which aims at fostering an African-European R&D partnership. And EU Africa R&D facility is a flagship program of the EU Africa initiative, with an overreaching long-term goal for supporting an African-European collaboration. And this project is being developed by 6 partners, so University of Twente as the leader of the project. We have also CS Group France, CS Romania, Serco, TU Wien and Vito. And altogether, 6 partners are continuously contributing to the activities, which started 4 years ago and will continue for another 2 years. There are 4 main pillars on which EU Africa R&D facility stands. And that is continuously growing EU Africa members community with participants of our activities, but also of the research calls, stakeholders and collaborators and institutions involved in organization of the trainings in African continent. The second pillar is related to providing a cloud-based Earth observation data analysis environment to support researchers in accessing and utilizing Earth observation data. So the cloud computing platform has been developed, which is called Innovation Lab. And we also have and offer technical and financial support for 30 research studies to address African Earth observation research challenges related to water scarcity and food security. And the last activity is establishing a digital platform, digital capacity development platform, to provide domain-specific training, and it is established via Space Academy, where we provide face-to-face and online courses, webinars, training modules, and also MOOCs, so massive online courses. And here I also provide you links to the social channels that we have. So you can find us on LinkedIn, Blue Sky X, and YouTube, and also, of course, through the portal through which you registered to that event. Okay, so now I would introduce the problem of this webinar, the idea behind this webinar, and why we think it is needed to be provided. So there exists a wide variety of remote sensing applications in the context of agriculture, and possible applications include crop mapping, classification, but there is also other applications such as water resources consumption, yield prediction, crop condition and phenology information, but also about soil moisture and crops productivity. So particularly, there are three main applications that benefit from the fully polarimetric products, and those are namely crop type mapping by means of supervised or partially unsupervised classification schemes. Different crop types can be classified in PolInSAR images, provided that they exhibit different polarimetric signatures as a result of different physical properties. Then also we can use it for soil moisture retrieval. So using target decomposition approaches, the response from the vegetation and the underlying ground can be separated. So also to investigate the dependence of the radar signal on soil roughness and moisture. And there is also application on phenology monitoring. When the plants change, their physical characteristics as they develop also change, and then different stages can be distinguished and treated as different classes. So this is separated based on their polarimetric signatures. And maybe not all of you are very familiar with what is PolInSAR exactly. So we would start from introducing very briefly what and why radar techniques are useful for agriculture monitoring. So synthetic aperture radar, SAR, is the type of remote sensing that uses electromagnetic radiation in the microwave region of the spectrum to create images of a scene that represents different physical and biophysical characteristics than those available from the most familiar visible or hyperspectral optical images. A significant advantage of microwave radiation comes from its ability to penetrate cloud cover and even rain. So in addition, SAR sensors are active in that they transmit their own electromagnetic signal to illuminate a scene and are not dependent on the target being in sunlight. So SAR signals are also able to penetrate vegetation from some distance, so making remote sensing of the understory structure of closed canopy forests possible, forests or agriculture fields, whereas optical sensors are limited to the upper canopy structure only. They can also additionally frequently revisit the same area, so it makes them enabling monitoring of dynamic processes like urban expansion, deforestation, and disasters recovery that can be useful by standalone use of SAR images, or also particularly useful when complemented by optical methods. And it also provides the global coverage via missions such as Sentinel-1, RadarSat, and ALOS, about which we will talk later. So just very briefly, SAR is an active imaging system, as I mentioned before, and it transmits artificial pulsed microwave radiation to illuminate the area being imaged. And the microwave pulses interact with scatterers on the ground, which are some objects located on the ground, which return some of the energy. And this return may be recorded by the transmitting antenna or a separate receiving antenna, referred to as monostatic or bistatic configurations, respectively. And key distinctions from passive sensors, unlike passive optical sensors, which record reflected or emitted radiation from the sun, SAR actively transmits signals to capture the data. And there are three main factors that influence the strength of the backscatter received, and therefore these parameters are crucial to consider for any study based on radar images. And that is why I wanted to recap on this before we start the actual content. So those radar system properties that involve wavelength, antenna, and transmitted power, radar imaging geometry that also define, for example, the incidence angle, beam width, and also characteristics of interaction of the radar signal with the objects, like surface roughness, composition, terrain relief, including also orientation of the slopes. And we will now have a brief look at these concepts very shortly. So while talking about SAR polarimetry and PolInSAR, we need to refresh the knowledge about the SAR geometry itself. So you can see from this picture that SAR uses an antenna mounted on a satellite or aircraft that moves along a straight path, known as the azimuth. So it sends the microwave pulses at an angle to the side of the path, and the energy that bounces back, called backscatter, is recorded. And the time taken from the pulse to return helps calculate the distance to the target, called the slant range. And this distance is used to organize the radar signal into cells, allowing detailed imaging. So that is how the SAR image is produced. And SAR captures a wide area in relation to the optical images on the ground, called the swath width. And this can range from 30 to 500 kilometers for satellite sensors. And the angle at which the radar beam hits the ground, it's called the incidence angle, affects the strength and the quality of the signals received. So now about some more concepts of the radar. So those are the radar frequencies bands. So frequency in SAR systems tell us how many wave cycles occur in a second, and a wavelength is the distance that wave travels in one cycle. So these are grouped into bands, and SAR sensors are usually identified by their band name instead of the exact frequency or wavelength. And the choice of band significantly influences the information content of SAR images. And when you work with that data, you will see on your own. Especially when observing the vegetation. So the lower frequency bands like L and P band can penetrate vegetation canopies, providing information about underlying soil conditions and moisture content. Conversely, higher frequency bands like X and C are more sensitive to canopy structure and composition. However, the small canopy structures relative to the spatial resolution of spaceborne SAR can pose challenges to direct detection methods. And the use of multiple bands or the integration of auxiliary data can, to some extent, mitigate those limitations. Note also that Q, K, and Ka are the bands that are not used or rarely used in spaceborne sensors for terrestrial studies. And how the SAR works, it is also defined in that 5 basic concepts. So radar backscatter from tree or from the agricultural canopies, as you can see in that image, is influenced by the following factors. So first factor is the frequency. So lower frequencies penetrate deeper into the canopy, interacting with larger structures like trunks and branches, while higher frequencies, like for example X-band, primarily scatter off leaves and smaller elements. The incidence angle as the second concept, so it provides information about the backscatter that varies with crop height and leaf angle distribution. So the larger angles increase sensitivity to canopy structure and water content, for instance. Polarization, this is another concept that we will talk about more in detail later. So the cross-polarized signals capture volume scattering from branches and leaves, while the co-polarized signals, for example, horizontal-horizontal or vertical-vertical, are sensitive to trunk orientation. And there are also geometry that influences the signal received by sensor. So the complex structures with varying heights and densities, such as, for example, forest, lead to diverse scattering mechanisms, including multiple scatterings between branches and leaves. And regular row geometry in crops like corn creates anisotropic scattering patterns, affecting radar signal attenuation and phase shift. And then we have vegetation dielectric constant, which defines, for example, when there is high water content in leaves, the dielectric constant increases, enhancing backscatter at higher frequencies. When it is low, it is the opposite, as you can see also in that picture. So now, I do not know if everyone of you is familiar also with the polarization, but polarization is some metric that is very much useful in polarimetry, as its names suggested. So polarization, what it is, it describes the orientation of the oscillating electromagnetic pairs perpendicular to the direction of travel. And polarization may be linear, circular, or elliptical. And in such systems, linear polarization is typically used, though sometimes circular polarizations are gaining tractions in some modern systems. And how it works. So in SAR, polarization is labeled with 2 parts, one for the transmitted signal and one for the received signal from the sensor. For example, the VV polarization, as you can see in that image, tells us that the wave is sent out and received in a vertical orientation. The VH tells us that the wave is sent vertically but received horizontally. And then we have also HH and HV, which is exactly the opposite. So the transmit is in the linear horizontal and receive in the linear horizontal for HH, and for HV, transmit is in the linear horizontal and receive in the linear vertical direction. And when the transmitted and received polarizations match, so for example, when we talk about VV and VH polarizations, it is called a co-polarized image or data. When they are different, for example, VH or HV, it is called cross-polarized. And these terms are very important because we are going to use them in the PolInSAR techniques as well. And using just one polarization provides one-dimensional information about the surface or target. So mainly by varying degrees of brightness, as you can see in a standard SAR picture with single polarimetry. While useful for distinguishing certain targets, collecting more than one polarization can be advantageous. And we can also see how. So multiple polarizations and wavelengths combinations provide different and complementary surface information. So a system that uses both vertical and horizontal polarizations has 4 polarization channels, which are HH, HV, VV, and VH. And single polarization consists of either, as you can see in that table, HH, VV, VH, or HV. Then the dual polarization is a combination of the two, so HH and VV together, or HH and HV together, and this provides more information about surface features compared to single polarization. And quad polarization refers to a system that has combinations of all. And this gives the most detailed information about surface properties, but requires higher power and limits the swath width due to higher processing needs. And then when we have these concepts clear, we have also something like compact polarization. So the transmits, it refers to data or to the product that comes from the satellites that transmits one polarization, usually circular, and receives 2 linear polarizations, H and V. And it is more efficient than a quad pole and allows for a larger swath coverage while still offering detailed surface information. And this is used in more modern SAR systems. So compact pole satellites include, for example, ALOS-2, RISAT-1, and SAOCOM, that are examples of satellites that use compact polarization. And also quad pole satellites are RADARSAT-2 and NISAR upcoming mission from NASA. So those are the examples of satellites capable of quad pole mode, transmitting and receiving in all 4 polarization combinations, so providing the most detailed information about the surface. And another concept to get familiar with is the copole phase difference. So it measures the difference in phase, so the wave's position in its cycle, between the 2 copolarized signals, typically HH, horizontal transmit and receive, and VV, so vertical transmit and receive. And it is used to understand how the radar waves interact with the surfaces. And here in this graph, you can also see how many studies have been using different polarization modes. And as you can see, the most useful is dual pole, but this is also because of the Sentinel-1 providing data sets which are in this polarization modes. So Sentinel-1, as providing free and open global coverage data, is one of the mainly used sensors in crop mapping. That is why you have this a very big number of studies that used this one for investigating or crop mapping. Okay, another concept to establish is the phase. So the phase describes the exact position of a wave within its cycle, as we said before, and it is measured in angles. So described as degrees or radians. And it is often represented using complex numbers in interferometry. So it measures the difference in phase between the 2 radar signals captures at slightly different positions or times, as you can see at this image. So in polarimetry, it represents the relative timing between horizontally and vertically polarized waves. And phase difference is impacted by the structure of the target. And some practical examples. So phase information is always available in single look complex data products. So when you search for some polarimetry data, you must search for SLC level of product to be able to extract that phase information, which otherwise will be lost, like for example in Sentinel-1 ground trench detected product. There is also another concept that is backscatter, and backscatter in SAR is defined as the energy that bounces back to a SAR system or to the antenna after hitting a target. So like vegetation, for instance, or other objects on the surface. It happens due to scattering, which spreads energy in all directions, including back to the radar, unlike reflection, which redirects energy in a specific direction. So there are three main types of scattering, as you can see from this image on the left side. So we have the surface scattering that happens on flat surfaces like bare soil, double bounce scattering that occurs when the energy reflects between a flat surface and a vertical structure like a tree trunk or building, and volume scattering that involves multiple bounces within a 3D structure, like for example tree canopies. And backscatter depends on surface features, as we said. So the variety of plants and their physical features like leaf size, direction, and density influence this backscatter power. And the presence of lower vegetation as well, but it also depends on the wavelength used and therefore how deep it can penetrate. So for instance, from the previous slide, as you have seen, that different wavelengths, different SAR bands have different power to penetrate through the canopy or through the soil, and this is exactly then present in the backscatter energy values. So now we reach the point to distinguish between PolInSAR and from which term it comes from. So first of all, I would like to talk a bit about polarimetry itself. So PolSAR technique, as you can already guess, it consists of acquiring, producing, and analyzing various polarization states of the electromagnetic wave, allowing the measurement of complete target information. And fully polarimetric data is only provided in the single look complex products, as I mentioned before. And the PolSAR technique can be used to classify various scattering mechanisms in complex systems, and it's then able to decompose them to identify the basic objects that the scattering occurs from. So the polarization, the values measured then from the different polarimetric channels, as we discovered before, are then organized in the form of a matrix known as a scattering matrix. And you can see a simple matrix here down in this slide. And it is available in the radar images and is dependent on the geometry and the orientation of the object, as well as its geophysical characteristics like surface roughness, moisture content, etc. And the scattering matrix that is obtained for each pixel of SAR image constitutes of 4 elements that are known as the complex scattering amplitudes. And then we have also another concept that is called coherency matrix. And this is a 3x3 matrix, which is denominated with the letter T, and it is able to extract polarimetric parameters of complex targets such as forest or vegetation. And this results in 9 parameters that contain the physical property of the target. So then the composition of the coherency matrix results in scattering powers that analyze the surface, double bounce, and volume scattering taking place in a distributed target. And those targets then generates then these targets generators can be used to create color this image, as you can see on the right side, which can be analyzed on how much these different scattering components contribute to the total backscatter and then provide RGB image even. In this example, you can also see a polarimetry imagery from the airborne UAV SAR instrument obtained over California. And horizontal and vertical polarized signals were transmitted and then resulting backscatter signals received, resulting in these 3 channels of imagery. So when these separate images are colorized and overlaid, details of different surface textures and features can be distinguished, as you can see. Then we have the concept of InSAR, so SAR interferometry. And this utilizes the information gained from the phase difference of the 2 images. And the phase difference image that is generated can also be called an interferogram. So the SAR interferometry is a method that utilizes the coherent nature of SAR images, so to measure very small displacement of the ground surface, like vegetation deformation or displacement, like earthquakes or subsidence. And this technique involves analyzing the phase information of radar signals to detect changes in the distance between the satellite and the ground. However, it can also be used to measure vegetation parameters, particularly vegetation height and biomass, by analyzing the phase difference between SAR signals that have interacted with the top of the canopy and the ground surface. And this capability is particularly useful in the presence of thick canopies, such as the rainforest. So to create an interferogram, 2 SAR images of the same area are taken from slightly different positions. For example, this is called a cross track, or from different times of the acquisitions. And the amplitude of the product gives the coherence, which indicates a small similarity, a signal similarity. And the phase difference between the images provides information about changes in distance, height, or surface deformation. And this together builds up in the interferogram, as you can see. And now we came to this crucial point. So what is polarimetric SAR interferometry? So this is a very crucial technique for vegetation properties, and for example, such as forest height or biomass, as well as for monitoring snow and ice thickness. As the name suggests, it combines 2 radar technologies, polarimetry and interferometry, and it gives the potential to separate in height different scattering processes occurring inside one resolution cell. And it requires more than 2 SAR images with controlled spatial baseline and minimized temporal decorrelation. So interferometry allows height allocation within the resolution cell, but cannot distinguish between different scatterers. And polarimetry distinguishes between scatterers, but does not provide height information. So to avoid the temporal decorrelation, the 2 images should be acquired simultaneously, also known as single pass configuration, and to provide this valuable information to separate and to get the information about different height of the vegetation and monitor agriculture. So when we talk about PolInSAR, we are talking about, as we mentioned before, about different matrices that organize the backscatter energy and the information that is providing by the single pixels. So there are two different concepts. First one is the covariance matrix. And the covariance matrix organizes the backscatter data collected by PolInSAR system across different polarization channels and reflects the scattering properties of the surface and shows how polarimetric channels are related. And it helps to characterize scattering mechanism, but requires also the composition techniques to extract the parameters to be interpreted, such as entropy or anisotropy. But I will not go into detail in here right now, because this is a content for another webinar. Coherence helps monitor crop growth, detect changes in vegetation, and assess field conditions, for example. It can, for instance, also identify areas with healthy crops versus those affected by harvesting, plowing, or stress. And another concept is the coherence matrix, and in that case, it is denominated by T, as we have seen also in the previous slide. And this concept is very fundamental because it tells us how similar the radar signals are between the two images. The coherence matrix measures the similarity or consistency between radar signals across polarimetric and interferometric channels, and it provides also information about surface stability or changes over time. And the high coherence means that the signals are stable and consistent, while low coherence indicates changes or disturbances in the surface. So in short, the covariance matrix organizes scattering data across polarization channels, while the coherence matrix measures how consistent signals are between images, enable interferometric analysis. Then, while talking about PolInSAR, we need to consider three important problems, which we already mentioned, but now we will also a bit investigate deeper. So if you remember the slide about scattering from different surfaces, as summarized in that figure, these approaches employ a model of vegetation scenes formed by two layers. So we have on the left side, we have scattering from non-vegetated surfaces, so from bare soil, for instance, and on the right side, we have vegetated surfaces, which is also defined as vegetated volume. The scattering from ground is localized at a single point in the vertical coordinate, as you can see from the image, whereas the scattering from volume is described by a scattering function f from z. So you can see here on the right side a function and how this scattering works from the vegetated surfaces. And but in agriculture, different model for polarimetric interferometry SAR has been introduced to address the radar interaction with both volume and surface in the underlying soil. So to characterize different physical properties of soil and canopy, this particular oriented volume over ground model was proposed to relate these interferometric observables at different polarizations and by baselines, as you can see from the image. So the key assumption of this model is that it is suitable for a wide range of crop types and growth stages, and as it accounts for the polarization-dependent effect introduced by the orientation, stalks, and leaves. And vertical variation of scattered power in the polarimetric channels for a volume layer or of height above a ground layer at a reference of height z from z0, as you can see in that graph. So this model requires multi-baseline observations. So it requires multiple observations to be implemented. And it is useful for monitoring seasonal changes in agriculture canopies, correlating with, for instance, NDVI for crop stage analysis. So this function is also displayed here. I also provided you some references to that model, but it is basically used in most of agricultural studies. You can also check these references to ensure that you understand that. I would not spend too much time on that model, but as you can see, this volume structure function and the ground scatterers are placed in that model to make sure that both parts are represented while describing the agricultural crops. So, for example, here we can see one of that applications that uses that model. So, in the image here taken from the ESA polarimetry course taken place in 2023, we can see the differences in phenological stages of the plants as recorded by the fully polarimetric product. And the red line here on the graph represents the height estimated with PolInSAR, and the dashed line represents what was measured on the ground. And you can see that you can see a consistent match between the estimated and measured values, allowing to follow the full phenological stage from the beginning to the end of the growth cycle of the plants. And this estimates also reflect the actual ground conditions. So if the field is not homogeneous and some crops bend, this will be also reflected in that height estimates. So now this was quite heavy content, I would say. So now I wanted to just put in place some of the concepts that I was talking about and put it to the table that you can also understand what are the key features and how the forest and agricultural vegetation is represented usually in PolInSAR. So first of all, the differences are in the canopy structure of the two land covers. So agricultural canopies are typically thinner and shorter, and these canopies are also often sparse or short, such as bare fields or young crops, and this makes them more sensitive to radar signals, especially when vegetation is sparse. But with the forest canopies, we do not have these problems because those are the complex vertical structures. So they significantly attenuate radar signals, making ground reflections less dominant. Then we have useful for monitoring of rapid changes in agricultural canopies are the short baselines. Such as in crop growths and phenological stages over short periods. So the short baselines are useful for the agriculture. And in the forestry, on the other hand, those are the more suitable are the long baselines because the changes are relatively slow in forest environments over months or years. And larger baselines are needed to enhance sensitivity to thin vegetation layers, while moderate baselines suffice for tall forest structures. There are also differences in modeling approaches. So the modeling for the agriculture is more abstract due to the variety of crops and plant structures. However, when we talk about forestry, it is well established. So, for example, the model like random volume over ground or RVOG are effective. And this random orientation of 3 branches leads to isotropic volume scattering, simplifying the modeling process. With respect to anisotropic propagation due to organized crop rows, for example, in agriculture, that affects scattering behavior. Okay, so now we went through the content about the PolInSAR and how it is used, and I would just briefly go through some PolInSAR missions that you can investigate straight after this webinar, because those are the missions in orbit that you can also investigate for your applications. So starting with the first one, we have TerraSAR X and the Tandem X that are 2 missions developed by German Aerospace Center and launched in 2007. And they have experimental quad polarization, but primarily operates in single or dual modes. And Tandem X specifically, it specializes in interferometric digital elevation model generation rather than polarimetric applications, but TerraSAR you can investigate for the polarimetry. Both are operating in X-band with 11 days of revisit cycle. And then the next one is ALOS-2 and ALOS-4, which are developed by the Japanese Aerospace Exploitation Agency, JAXA, and they offer quad polarization in L-band with advanced capabilities for forest and disaster monitoring. Sentinel-1, on the other hand, is developed by ESA, and it provides dual polarization data in CSAR band suitable for large-scale monitoring. We have also RadarSat-2 that supports fully polarimetric data and is provided by the Canadian Space Agency in C-band as well. And SAOCOM SAR observation and communication satellite, which focuses on soil moisture and agriculture monitoring with L-band dual polarization. And talking about their use in the studies on agriculture, so several studies used multiple sensors within a single publication, as it was reviewed in that review that I provide you a link here down in this slide. So those are the number of studies that have been investigated between the year 2011 and 2021. And they provide a number of studies with the use of different SAR satellite missions. And as you can see, most of the literature provides the results of the application of RadarSat-2 and Sentinel-1, which is also understandable because of their global coverage and easy access to the data. For example, SAOCOM, that is hard to get, and it's provided by the Argentinian Space Agency, is not very well used in that studies, but the number of studies is growing. So this was just as a sneak peek to something that you may be interested in on how this different satellites are applied. But we also cannot forget that the availability of current data and the launch of new missions will significantly enhance the role of interferometry and polarimetry in remote sensing and in agriculture applications as well. So there are few upcoming missions that we expect to see soon in the orbit. And first of this is biomass, which is developed by ESA, so European Space Agency, and it will be the first mission to systematically implement PolInSAR and polarimetric tomography working in P-band, so providing us with even more details on the forest structure and biomass. NISAR is another satellite mission that is developed by NASA and the Indian Space Research Organization in cooperation. to monitor the changes in the Earth's surface associated with the movement of the crust and ice cover. And it will be operating in S and L band. ROSE L will be another L-band synthetic aperture radar, which will complement the existing Copernicus C-band SAR systems and improve imaging in areas with dense vegetation thanks to its longer wavelength. And last but not least, we have also proposal of mission Tandem L, which is German Aerospace Center mission. And in its LSAR modes, it will be used to complete other important mission goals, including global measurements of forest biomass and temporal variation of the forests, as well as glacier motion and melting. And where to find this data? So here I also provided a list of different satellite missions and different data types products that they provide with the access, so with the name of the portals through which you can access the data. I will not stay long on this one, but here I also provided a link to the main data access points. So for example, one main data point for the Copernicus data space for the Copernicus data is the Copernicus data space ecosystem that provides Sentinel-1 products. But ESA also provides some sample data from the third-party missions, which were mentioned before. So for example, to ALOS or Tandem X, Tandem TetraSAR X, and also some RadarSat-2 sample products. But there are also a collection of ALOS products, for example, on Africa with African coverage. I took this image from the ESA Earth Online portal, to which everyone can register and acquire a product from there. There is also NASA Earth Data Search, and as well national space agencies and industries provides some of the data. So here, for example, you can have a preview of the ESA Earth Online portal, which you can investigate on how to access them. Some of them have open access, as I mentioned. Some of them have only sample data sets, but you can still work as well on the sample and see if you like it or no. So, and how you process, for example, the data. So there is a toolbox that has been developed by ESA, European Space Agency, for the scientific exploitation of polarimetric SAR data, and it supports various types of SAR data, including PolSAR, PolInSAR, PolTomoSAR, and PolTimesSAR. PolSAR Pro includes functionalities such as speckle filters, decompositions, parameter estimations, and classification and segmentations, and it supports what is the most important, the use of satellite products coming from different satellite sensors, not only European ones. So it supports ALOS, Cosmos Skymet, RadarSat-2, TetraSAR X, and Tandem X, and it is free and open to download both on Windows and Linux. And it is a standalone application. So there is also installation process is quite nicely described, and there is a community forum available in case of questions or doubts. And it will also support future ESA biomass mission and can be used as well as in processing and analyzing other polarimetric data. It works both as a desktop and also in a command line tool. Another one is ESA Snap Toolbox, which stands for Sentinel Application Platform, but it also supports not only Sentinel products like Sentinel-1, but also other sensors, both optical and microwave sensors. And it includes tools, for example, for polarimetric processing, such as matrix generation, speckle filtering, and decompositions. And it works also with coherency and covariance matrices as input. As you can see also in this graph, this is like an example of a workflow that you can also investigate using SNAP. It is also free and open to download, and I pasted the link to the website here. So all these workflows consist of many steps, and here I only provided you some of the sneak peeks from the case studies on how the polarimetric interferometric SAR processing workflow looks like. So you always work with multiple images, and in the case of PolInSAR, you have interferometric and polarimetric information that you can use, for example, for tree height estimation or crop height. The second one wasn't that much investigated in the literature, but of course you can find some studies on that. So here I also prepared some views on the case studies which have been developed over the years. As I mentioned, PolInSAR technique is quite new. So this, for instance, was the first study published in 2016 by Lopez Martinez, who also is developer of the PolSAR Pro tool. And it is a first publication on rise height with the use of PolInSAR data without any auxiliary data. So it was the first spaceborne vegetation height study that used tandem X data from the DLR. And this demonstrated that the production of accurate rise height estimates is possible with a small error. And the tandem X data is showing that the performance of over 3 different test sites separated geographically and with different rice varieties and along the whole cultivation campaign from sowing to maturation stage. And here, the rice is the most investigated maybe crop because of its evident socio-economic interest, but also due to its well-studied radar response. For example, you can also very well detect the ground and the rice plant from the radar signal, because it is very likely that there will be water on the ground, so it separates the signal very well. Another study, for example, shows the water hyacinth in Lake Victoria in Africa. So here I selected this study because it nicely shows how to use the Sentinel-1 data to map and monitor water hyacinth cover. And it also separated in a clear way with 98% of accuracy, a clear and infested water. So you can also use the Sentinel-1 dual polarization data to explore such cases. This study, for instance, was conducted in a catchment located in the northern west part of the Republic of Benin. And like other parts of West Africa, agriculture here is mainly rain-fed. And here the analysis was conducted with the rapid eye image with also combination of TEDASAR X. So as I mentioned before, very often the optical and polarimetric data are combined together, and they were able to by using TEDASAR X data, particularly VV polarization, to enhance the separation of specific crops like rice, cotton, and maize or sorghum, and addressing challenges posed by complex cropping systems and fragmented landscapes. And there is also they also obtained quite good accuracy. So the accuracy of classification by integrating this TEDASAR with multi-temporal rapid eye images improved the accuracy of about 10 to 15% through the cropping season. Here another example. This is from the forestry. So along the study area that is situated in Gabon, along the western coast of Central Africa. So in 2016, a collaborative effort between NASA and European Space Agency and the Japanese Space Agency led to the AfriSAR campaign in Gabon. And this study uses airborne multi-base PolInSAR data with models like random volume over ground and other models for forest canopy height. And you can see that it is integrated also with LiDAR, and it also shows like how different models performed on this forest height estimation. Here another robust deep learning approach was developed in the same study area or similar, because this was the data sets that they had. So the model was trained and tested over 5 tropical sites in Gabon from the AfriSAR 2016 campaign. And they proposed this model demonstrated very strong performance with the bias of 12 centimeters to estimate the forest height. And it was a country scale canopy height map at 25 meters resolution. So it is quite potential tool. Just, I would like to excuse myself for getting this that long, but just some take-home messages and conclusions. I hope you did not fall asleep during this webinar, but as I mentioned, it is quite a complex topic, so that's why I wanted to go through all the concepts and make sure that you understand. And it was maybe less practical than usual, but this was planned to be an introduction also to our upcoming online course, which will happen soon. So just to conclude, that PolInSAR demonstrated as a very sensitive technique to vertical structure and distribution of scatterers within the canopy, and it can discriminate the effects from various crops and soil properties as well. And the use of PolInSAR for agriculture is unfortunately understudied and poorly represented in Africa, but this is also due to the availability of data sets and non-open, not always open data sets worldwide. But with increased numbers of sensors becoming soon available, utilization of these diverse frequencies, like for example XL and P band, will provide new opportunities for the research. So this would be the end of the webinar, but I would like to just mention to follow the portal that we have, and because we have plenty of planned activities which will be coming very soon. You can see, for instance, here that we have now application open for 40 hours online course on PolInSAR, where we will provide you theoretical lectures, so registered lectures with some lectures notes, but also practical sessions. So it will be also a practical assignments will be available, and this is 4-week online course that you can apply from now until 9th of May, and it will take place between May 26 until June 20. So in 2 months, you can start learning more about this processing and applications of PolInSAR. We have also another online course which will happen soon, and the registration is until April 3rd of April, and it is on high-resolution crop monitoring for food security using EO, and it will be provided by Vito, so it will be as well structured as 40 hours online course with some online support as well from the teachers. There are also face-to-face courses which are in the list, so please make sure that you do not miss any of those opportunities. And all the webinars that are coming up with new topics will be published in our YouTube channel, to which you can find also QR code in that presentation. So I would like to thank you very much for participation. If you have any questions, please let me know. And I will now maybe stop sharing for a moment to just see the chat. I think the webinar was registered, so the registration will be provided in a few days on the YouTube channel. So please make sure that that you also check our portal and to see that and to rewatch this recording version. For those of you who wants who needs to have access to the presentation, please write me an email, and I will distribute it also as soon as possible. So I will just share right now I will just share my email address. So it's ewelina.dobrowolska@serco.com. You can also take a screenshot of that. Just a moment. I will reshare my screen because I think. So I think you can now see the entire presentation. To just show you my my email address. About the soil organic carbon with radar data, I can also investigate on that. There were some studies, but many of those studies were using only some airborne polarimetric INSAR data sets. That's why I didn't bring all of them here. But of course, if you are interested, please write me by email, and I will also provide you some links. I will also type my email address in the chat. So. Okay, and yes, I mentioned that PolInSAR data for Africa is very limited currently, and how the African researchers can explore its use, because I would like to understand more and possible get hands-on experience relevant to Africa without wait for long-term developments. Or yes, I I don't know what was the end of this message, but yes. So this is also some opportunity for you, because during this online course, we will try to also implement some practical sessions. So you will have practical assignments with the data for Africa. And for example, ALOS2 provides some data sets that can be discoverable over forested areas in Africa. It is not maybe that much explored for the agriculture applications, but still the number of researchers are going. So then, of course, you can get some hands-on practice. There are also plenty of materials online coming from, for example, ESA polarimetry courses that are developed each 2 years. And you can access some training materials and start exploring it, because this needs a bit more technical expertise and technical knowledge that maybe in some specific regions are not supported yet. So, for example, with the optical sensors, we have plenty of missions and plenty of data sets that are free to use, but not it is not applied to polarimetric products. So the correspondences between different polarization channels, yes, they are chosen randomly. You can also change the colors. It is just RGB representation as in any image. So you have to assign them, but then you need to, of course, for interpretation, you need to know which one you assigned to which backscatter channels. So the cultivated areas in Africa, this I do not have so much experience on the particular regions in Africa, but of course, the cultivated areas in Africa not always are organized in rows. So sometimes when you do not have this structure, then you would use different models for specific crops. So in the registration form, what you would like to, you would need to place is your motivation. That is crucial for us to evaluate the application. And as I also showed you before, the application for the online course is open and will remain open until 9th of May. But the prerequisite of this online course particularly is the previous experience on the SAR processing and SAR image interpretation. So if you have some background in Earth observation and specifically in radar missions, then you can, of course, apply, and we evaluate your background and your motivation to participate in that course. Because we have many applicants and we have only 75 places, so we must ensure that we get the correct users onboarded. Okay, I think that is the end. Yes, I can share the the link. So I will just very quickly go to the portal and okay. So that's the description of the course, and there is application form which you have to fill to register for the course, and then we will evaluate your applications. So thanks a lot, everyone. I took it a bit longer, so we are 3:15, but I hope you were not bored. And Thank you very much. For those of you who would like to receive the webinar slides, please write me an email and I will forward it to you. And of course, I would like to thank you once again. And I hope to see you all in this upcoming online course, where you will have more chance to interact, because we will have also live chat, live sessions, and also chat in the Moodle platform. So this will be supported. So thanks a lot, and have a nice afternoon.